So my name is Athina Koustenis. I work at Paris Observatory in Meudon in France. So I am a researcher, a planetologist, working in the outer solar system essentially. Thank you very much. It's a pleasure to be here today. As you just heard, my name is Athina Koustenis. I work at the Paris Observatory and I'm living in France. So as this indicates, I'm an immigrant. Moving between different countries. I can say hello in 10 different languages, but only understand 4.5. So, kalimera, hello, guten Tag, konnichiwa, ni hao, all of this. And I'm here today to follow up. Buongiorno, sì, buongiorno, buon dias, all of that. Hey, well, yeah, we have a large community back there from Spain? Yes. And others, okay, and Italians and everybody. I don't want to offend anybody. But I'm going to follow up today on the previous talks that you heard. We're still going to be discussing habitability. I'm going to be saying what we think is habitability from the perspective of an astronomer. And then I'm going to continue on the other worlds that weren't mentioned previously. So when we look at habitability and habitable conditions, this is something that the astronomers discuss and describe as the measure of a planet or a natural satellite, because we're going to be discussing mostly satellites, the potential to develop and sustain life on or in. And so this is going to be very, very important. And of course, we have some sorts of indications and descriptions of what this means, but the habitability criteria is, as you see them here, the extended regions of liquid water, because we have to extrapolate for life from what we know on our own planet. You have to have conditions favorable for the assembly of complex organic molecules, the famous SNOPs. And this is basically the nutrients. This is basically your food, okay? Then you have to have all of that with some energy. You need energy to be brought into the system to be able to get the reactions that you need to sustain metabolism. And of course, you need a stable environment. A stable environment is something that is very, very important. So, back in 2009, we did some studies with colleagues of mine, and we tried to classify what we call the habitable worlds. And you see here, class 1 is one planet that we know, Earth or Earth-like objects. These are habitables that are suitable for the evolution of higher kinds of life on their surface or somewhere else, but basically on the surface. Then you have class 2, where you have the inner and outer edge of the habitable zone that I'll show you in a minute, where microbial life may have evolved, habitats may have existed on the surface or the subsurface. They could be still there today. That's why we're exploring planets like Venus and Mars. Class 3, now we're moving beyond what we call the ice line, and we're looking at life forms that may have evolved to populate subsurface liquid water oceans. And what I'm going to be very much discussing today is class 3 and class 4, which are looking at liquid water and the possibility of oceans of liquid water underneath the surface, because it's not only on the surface that you can have the conditions for habitability. And we're going to be looking at the satellites that we have around giant systems. And of course, looking at class 1, the only planet we have our knowledge of life existing on it is the Earth today. And you can see here what are the characteristics of the Earth in terms of habitability. You have plate tectonics for the energy, liquid water existing in 3 different states, liquid, solid, and volatile, gaseous form, a small amount of water. These are not huge water planets. Dense atmosphere, magnetic shielding. Magnetic shielding, if we're here today, is because we're shielded from the solar irradiation and from cosmic rays and from all of this due to a magnetic field and good stability, of course, on our planet. Otherwise, we wouldn't be here. And then we have the class 1 and class 2 that I discussed. And what happened? What went wrong with class 2? What went wrong with class 2 is that the time dimension is there with crucial. It could be migration due to star evolution that forbid the planet from developing life. It can be its location with the habitable zone with time. They could be the weak magnetic fields or no magnetic fields, the dynamical evolution, and also atmospheric loss processes. And all this has to do with how it evolves with time. So I know this is your field, Philippe, but you mentioned Mars this morning. So usually people for habitable worlds in the solar system look to Mars. And of course, we've had the fabulous launch of the ExoMars mission, the ExoMars 2016 mission, which is an orbiter and a descent module. It went off on 14 March, and I had heard just a few days ago it's doing fantastically well. We've got the signal, everything is working. So this is a fabulous mission that is doing two things. It's doing science, and it's also doing technology demonstration, because it has a module on it that will be descending on the surface to demonstrate that the European Space Agency can now land things on the surface of Mars. But we have also quite a lot of science there to study the Martian atmosphere for evidence of biological gases, including methane. So, coming back to the habitable zone. So both Michel and Philippe mentioned habitable conditions. So in the solar system, here's our solar system, here's the sun, here's our planets. We always think of the habitable zone as this light blue region here where you have the Goldilocks example, where you have Earth right in the middle, perfect place, perfect timing. You know, we're the lucky ones, okay? And so here's the Earth here, and then at the edge here, these poor cousins. You know, on the one side, Venus, on the other side, Mars, and these two poor planets struggle. You know, they would like to have life. Now, they don't have it today. For Venus, it's for sure. If you want to get toxic, you just go there, you know, acid in the atmosphere and all that stuff. And for Mars, we keep trying. You know, some people put seismometers on it. You know, they're trying to find some evidence that maybe there's something possibly underneath the surface, you know. So we're struggling there. But nobody, you know, is thinking of what's going on the other side. So this is the famous snow line here. And the famous snow line is where people thought, okay, guys, no habitable conditions beyond that. All right, why? Because you cannot have liquid water. And then, some time ago, this thing happened. This thing is called Enceladus. This is a tiny little moon, 10 astronomical units away from the sun. And this little thing is spurting water. It's got geysers of water ejected in space. So people are thinking, oh my God, you know, how can you get water geysers 10 astronomical units away? Well, probably because you can have liquid water underneath the surface. And they started people thinking this, and the fact that around Jupiter, we also got indication that the surface of some of the moons probably showed evidence for plate tectonics. And all of this started people thinking, well, maybe underneath the surface of these moons, there are what we call hydrospheres. Hydrospheres are these blue lines that you see here underneath the surface. And maybe this indicates that we shouldn't stop thinking of the habitable zone here, but that we could extend it to this other blue area here all the way to the outer solar system and just look for evidence for habitable conditions underneath the surface and not on the surface. And of course, the habitable zone varies with the mass of the star, as Michel explained before. The bigger the star, the further away the habitable zone can be. The smaller the star, the closer the habitable zone begins. But this is what we're going to be looking at today. We're going to be looking at deep habitats, not surface habitats. So we're going to be looking at classes 3, 3 and 4. Okay, so I'm going to be talking about moons, but I'm going to be talking about large moons, essentially, around Jupiter, 3 of the Galilean satellites, Europa, Ganymede, and Callisto. And around Saturn, we have Enceladus, I just mentioned, and Titan. These moons have been explored by space missions so far. Galileo mission which did operate from 1995 to 2000, and the famous Cassini Huygens mission here, who is still in operation in the Saturnian system, going around Saturn for another couple of years or something like that. So we have some observations, but in my talk I'll be mainly focusing on future exploration. But I wanted to start giving you an idea of what we see in the solar system around Jupiter. So Jupiter, usually we call it the mini solar system. It's really a system on its own. You have the huge planet here, and you have the moons. This is a giant planet. You have the largest object in our solar system, if we could see it, would be the magnetosphere around Jupiter. It's huge, it's enormous, and a lot of people are studying, those who get excited over electrons and plasma and magnetospheres, things like that, adore, really love looking at this. But for me, the major kick comes out of studying the four planets, the four satellites around this giant planet. These are the Galilean satellites. And the important thing about the Galilean satellites is that they have a lot of unique features. These features were explored by the Galileo mission. You can see here that did a few flybys of Jupiter and ended its mission in 2000 and provided basically all the figures, all the images we had of these moons around Jupiter that we used in our scholar manuals up until a few years back. I don't know if you remember, we had this image of Jupiter and this image of Saturn, all of that taken by the Voyager missions, and we had a couple of pictures of the satellites. Now we've gone way beyond. I mean, the recent exploration of the solar system has brought us a lot of images, a lot of new data, all of this, of course, on Google, but a lot of it in accessible to students. So, the past exploration in the Jupiter system gave us snapshots. Snapshots. Why am I saying snapshots? Because when you look at a planet, contrary to a star, you have changes. You have dynamical changes in the atmosphere, you have changes on the surfaces, but you also have changes due to seasons, right? So we're sitting here 5 astronomical units away from the sun. And Jupiter revolves around the sun. So basically it changes, and everything that goes around it changes with time. The atmosphere changes, and so we need continuity of the data that we have gotten up to now to look at new features in the atmosphere, to see how the albedo, the color, the circulation, the temperature, the composition change with time. And we have atmospheric regions that have never actually been looked at. As concerns the satellites, 3 of them I'm going to be focusing on is Ganymede. So Ganymede is the largest satellite in our solar system. Which is the second one? Yes, Titan, good. So we'll be talking about Titan later afterwards. Ganymede is the largest satellite in our own solar system, and would you believe it, it has not been explored. It has not been explored as much as it should, because not only it's the largest one, but it also has a magnetic field. And remember I told you magnetic field is very important for habitable conditions. It also has a lot of crater morphology of interest to geologists on the surface, and it may have a deep ocean underneath the surface. You can see here this blue line. This is ice, by the way, because all of these moons are basically ice. But underneath the surface, you may find the conditions for having and sustaining liquid water. So this is the best example for a liquid environment, we think, and I'll tell you why we think there is a liquid ocean underneath the surface, but trapped between 2 ice layers that are shown here. Callisto is the second largest. It's a good place to look for impacts. The surface is very heavily impacted. We don't know if there has been differentiation here in the middle. You see here we have a core, and then we have the magma here, and then we have the ices and so on. But we don't know if differentiation exists on Callisto, but it's a very good example for non-active probably ocean-bearing world. You see here again, possibly the existence of liquid water underneath the surface. And Europa, of course, Europa was the first satellite that people have looked at to see if it was possible to have plate tectonics on the surface, all these ridges and gaps indicating possibly movements at the surface level coming from the interior, which is an example of liquid environment. But in this case, as I'll show you in a minute, it would be in contact with the core. So looking at the family of Jupiter, we have all these satellites shown here with the Galilean satellites. And the trick is to remember, if you're close to a huge, huge planet like Jupiter, you're going to suffer. Jupiter has a lot of energy, a lot of radiation that it's giving out, right? And the magnetosphere and all of these effects. So if you're poor Io, or EO, as we say in Greek, EO. So if you're this poor satellite, tiny little one, very close to Jupiter, what happens to you is that you get 400 volcanoes on the surface. You're boiling. So no point for looking for habitable conditions there. There's nothing that can exist. Okay, next one is Europa here. So Europa shows, as I said, indication. I'll show you a little bit more in detail in a second. Indication of movements at the surface level. You can see them here in colored contrast or the real images. So there's something happening underneath the surface. Ganymede here, look at the craters that we have, and the black and white terrain on the surface, and Callisto, heavily cratered. So these satellites, these other ones, all indicate the presence of a hydrosphere, that is liquid water, underneath the surface in different conditions, possibly directly in contact with the silicates of the core, possibly sandwiched between two ice layers. And in the case of Callisto, we don't know exactly what's happening in the center, but this is what we're trying to find out. So for Europa, what we call hyperspectral evidences is look at these bands and these ridges on the surface. This is a very tormented surface. But what this is telling you is that basically you have the red features here, and look at the white ones here. So what we think this indicates is that we have both movement from the interior coming up, and then also from the surface going down. From the surface going down is what we call subduction. So subduction is, you have these two layers of the surface coming together, and one of it has to yield, goes into the interior, the other one stays on top, and this is how we lose some of the surface on Europa. We lose it, we're missing it, so if you wonder what happened to it, it went underneath, it went to the interior. And other places like here, for instance, we can see that something has also crunched together, or something has opened up and has let material from the interior, preferably water, come up on the surface, or something has gone down. So there is a lot of indication for plate tectonics on Europa, but we still don't know what's going on the surface. So the usual way to look at the composition of a surface is by comparing what we have, the data. So the data here is NIMS. So this is from the Galileo spacecraft, and you can see the red line. And then you test it again, different kinds of ices, different kind of components. You see nothing fits exactly. So we don't know exactly what the composition of the surface is. We don't know how much ice we have. We don't know what kind of components we have. And so there is a lot of need there for exploring better what goes on Europa, because here we really have a very good example of possibly the presence of a subsurface ocean, warm, salty H2 ocean that you see here, in contact with silicates. This is the same thing that happens on our own planet. On our own planet, we have liquid water, the oceans, in contact with the rocks. So when this happens, you get something that is called the redox exchanges, and you create the energy that you actually need to make something like what we call serpentinization and hydrothermal activity. And this is black smokers. This is things that we have here on the Earth. And around these black smokers, you create, no, you don't create it actually, but you can sustain life and living organisms. You can have enough temperature and you can have enough energy. And this is what may happen here at the bottom. And you can see these weird creatures here. I'll say a little bit more about it in a minute. So this is a relatively stable environment. And we may have Europa as the best example currently, actually, in the solar system, imitating our own planet. And send a probe underneath the surface. And of course, you're all aware that this is just fantasy because the main problem will be the radiation. So before we can land on Europa, we have to solve the radiation problem. So this will take a little bit of time, but we are prepared. Now that we know that this may look like, we're prepared. All right, so now I'm going to turn to Ganymede. Less exciting. We haven't seen any creatures underneath the surface so far, but we still think that we have the presence of liquid water sandwiched between two layers of ice. And the water actually, in form of ice or in form of liquid, on Ganymede is very big. You can see here that it can be 30 or 50% in weight of the planet. And so this type of satellites is what we call water worlds. These type of bodies are huge in water, so we call them water worlds. So Ganymede is actually an archetype for what we call the water worlds that may be actually very common in the universe. So if we're looking for the chemical compound and the reactions that we have by contact with the silica, we don't have it here. Is it really needed? Is there some other way that we can create the chemistry? Energy, do we have heat transfer? Is there enough heat and exchange coming from Jupiter? We do have a stable environment. So we're looking at a satellite that has some of the characteristics that we like to find on a planet. And among other things, it has an induced magnetic field that forms from the interaction with the Jupiter magnetosphere and a conducting layer, for those of you who know how an induced magnetic field comes into place. It's because you have this interaction, and we think the conducting layer is probably this ocean, this water ocean underneath the surface. It also has a driven dipole magnetic field, and it also interacts with Jupiter's magnetosphere. So this is a very, very complicated system in terms of magnetic field that we have not today studied sufficiently. And we also have not studied sufficiently the presence of this wider and darker terrain on the surface. So again, as I said for Europa, if you have these bright areas, it may mean that it's a younger surface that comes onto the surface from the interior, from water flooding from the interior, now or in the past. So Ganymede is also a very exciting world. You have many places in the Jupiter system that are really worth going back to. The same holds also for Saturn. In Saturn, you have two bodies that have been very exciting to us, planetary scientists, in the past few years. One is Titan, and Titan is usually characterized as a frozen Earth. I like to think about it as a unique world on which you find several things and several indications on the surface of unique characteristics. Mentioning only, we have indications of cryovolcanoes, dune fields, same as we have on the Earth, created by a very, very light wind on the surface, moving ice particles. So it's not sand, it's ice particles. It's easier to move and to form the dunes. You have mountain ranges, and the two most important characteristics are that this is the only other body in the solar system where you have liquid exposed on the surface. It's not liquid water, it's hydrocarbons. But it's the only other place in the solar system where you have liquid hydrocarbons, hydrocarbon lakes, and channels, river networks exposed on the surface. And we are at 10 astronomical units. Okay, so this is very exciting. We also have a chemistry, I'll show you in a minute. This is the Cassini Huygens mission. I had the opportunity to work on the Cassini Huygens mission when it began, so in the 90s. I was a student, and I helped writing 3 proposals for 3 different instruments on the Cassini Huygens mission, hoping that maybe one of them would go on board. And today, I'm the happy co-investigator of 3 instruments on board the Cassini Huygens missions because it worked. And so we get data from these instruments, the spectrometer on board the orbiter, the temperature, the thermometer, and the density instrument on the probe, and also the famous DISR, that's the infrared spectrometer, radiometer, in other words, the camera. The one that took all the beautiful pictures you saw. So it's my team. And so we were very happy to get all the data here on Titan. Cassini also explored Enceladus. Enceladus was a huge surprise when we saw these geysers coming out of the South Pole. These geysers eject material 400 kilometers out in the space. So this is not a small geyser. It's huge, much larger than Yellowstone, much larger than anything we have on the Earth. And here you see, we detected it the first time with a magnetometer, and here you can see the images showing how it comes out of the South Pole. Here's the detection with the magnetometer because it bends the magnetic lines. And here is a picture of how these ejecta come out to space. And here is what we find in the geyser when we do an analysis. First, and among everything else, water vapor. So if you have water vapor ejected out there, it has to come from somewhere, right? Best candidate, all the models are telling us the best option for this is to come underneath the surface from a pocket of liquid water, coming through cracks to the surface, and then ejecting out to space. So you have to have liquid water underneath the surface, and you have to have it in the right conditions for hydrothermal circulation. You have to have convecting ice, but in all ways, you have to have liquid water underneath the surface. And actually, the material that gets ejected goes and feeds the E-ring around. See here the rings? It feeds the E-ring around Saturn. The other thing that you see when you do the analysis of the spectra from the geysers is all of these organics. So you have organic chemistry also, either on the surface or somewhere in the interior of Enceladus. So basically you have liquid water, you have organics, you have a stable environment, and you have energy sources, because otherwise you wouldn't be able to get this. You wouldn't be able to get this thing coming through the interior and going out in space. So very interesting object. Titan is huge. Titan is enormous in terms of how you can approach it. You have organic chemistry forming high up in the atmosphere, diffusing down. You have a very exciting surface with all the features I described before. You have a temperature profile very similar to what we have here on Earth, because in the lower part of the atmosphere, there is an effect that only takes place elsewhere on Earth that heats up the surface. So what heats up the surface on Earth? I'm doing what you do in school rooms. The greenhouse effect, okay? Because you have the clouds. In the case of the Earth, it's water vapor. On Titan, I told you there is no water outside, but you can replace it with the same thing that creates the lakes, methane. So methane on Titan is what makes clouds and haze and heats up the atmosphere to a balmy 94 degrees Kelvin. Who wants to go on holidays there? No? Okay. Anyway, very, very exciting similarities with our own planet. And then we think that underneath the surface, you may have this liquid water ocean. You also have seasons on Titan. Remember, Saturn goes around the sun in how many years? No, it's 10 astronomical units. Takes 30 years, okay? So because it's tilted the same way as the Earth, we get seasons. It's tilted, right? So we get seasons. So one season on Titan is, yes, 7.5 years, okay? 7.5 years of summer, 7.5 years of winter, 7.5 years of everything, right? Okay, enough time to go skiing, to go to the sea, but the most attractive thing on Titan is not the seasons. One day on Titan is 16 days, right? 8 days to sleep, 8 days to work, or something like that. So for those of you who say, I don't have enough in 24 hours to get my work done, okay, we'll move you to Titan, and there you'll have plenty of time, okay? So Titan, very exciting. I cannot sell it enough. Except to say that we also have this indication of an undersurface ocean. We have an organic-rich atmosphere, high pressurized, a silicate core, but we don't know if the ocean goes all the way down there. But the ocean is supported, the ocean theory is supported by measurements of the spin, the tides that we have, so all of this indicates a liquid water ocean. The probe, Huygens measured radio wave and low frequency measurements that supports the subsurface ocean theory. And here is a picture of what the interior would look like with the ammonia water ocean down here. We need the ammonia because you are at very cold temperatures. And what you put in your car in the winter, the antigel, is ammonia, basically, okay? So we do the same thing on Titan. This is how we keep the water in liquid form, all right? So that's why it says ammonia water. And this stays here. Probably there is an icy crust above this, but all of this indicates the presence of liquid water underneath the surface. So all of this is very exciting for Titan and for the exploration in the future. I want to say a few words now. How are we going to go and investigate all these things in the years to come? This is the current program. For those of you who were there yesterday, at the Union Symposium 5, you know, where we discussed the ESA program and the NASA program. This is the ESA fleet currently in the solar system with all the missions close to the sun, studying Mercury, Venus Express that finished this year. We have Mars Express ongoing, Cassini Huygens, and Rosetta, of course, I don't have to introduce, you all know what this is. But among the main missions in the solar system that have been adopted by ESA at the moment is JUICE. So JUICE is here. Up here, it's a major mission that is currently in implementation phase. These are all the pink missions in implementation phase. Here in light blue are the post-operation missions like Coyote, Gaia, and Proba 2. And here you can see in green everything that is currently still operational in the ESA program, like, for instance, LISA Pathfinder, about which you heard yesterday. So I want to say a few words about JUICE. JUICE is a fantastic mission. JUICE stands... Yes, I know. I told him to come and talk to you. I'm just going to say what's relevant to habitability. So JUICE is the Jupiter Icy Moons Explorer, and it's going to be looking very closely to the theme of habitability. Habitability is one of the themes that were important for the Cosmic Vision program of ESA, the emergence of habitable worlds around gas giants. And we are going to be looking at chemistry, energy, and water, because this is very important to look at conditions for planetary formation and emergence of life in the solar system. And what we call L1 is the first large cosmic vision mission that is going to be launched by ESA in the days to come. The launch is actually foreseen, as you'll see in a minute, in quite some time from now, but you all understand that we're always talking to you about something that will happen in a long time from today, because our interest here is to give you something to talk to your students about. So we're talking about a launch in 2022, sometime from now. We're going to take about 8 years to get there, and we're going to look at Europa and Ganymede. The important thing about this mission, it's its long duration. We're going to have about 3 years of mission in Jupiter, studying all the different objects there. And the important thing is that we're going to get, first of all, let me say, we're going to get 2 flybys of Europa. So why are the 2 flybys of Europa interesting? It's because we're going to be looking at these regions on Europa that may actually be what we call active regions, with a very small amount of ice on top that we can probably see through thanks to a radar that we have on board, a nice penetrating radar. And then we can maybe see the guys underneath, remember, in the ocean and see what's going on there. So it's very important to identify these 2 regions. And the other important thing is here in Ganymede. We're going to go and put ourselves in orbit around Ganymede for quite some time, actually, and the distance is going to be just 500 kilometers. So it's really something very important to realize that we are going to be actually helping out. If somebody wants to go and land on this object, we're going to be able to go and see how these things operate. Let me try to show you a little bit of a flyby of Europa, because this is going to allow us to identify the areas where maybe we will have the possibility to pierce through the ice and look underneath. So you see a flyby. We went in and we came out. This is a very close flyby. And the problem with a close flyby is, again, the radiation. Remember I told you before. So we have to go very fast. That's why you saw this thing fly in, take the measurements, fly out. Again, it's very difficult to have an orbiter around Europa, but we will have an orbiter around Ganymede, so that's very important. It's going to tell us everything, cartography of the moon's surface. We're going to look at the ice shell, the ocean, the deeper interiors, try to describe how deep is the ocean on Ganymede. What is the connection with the interior of the satellite? Look at the geology and the surface composition. The atmosphere and the ionosphere, they're very, very small, tenuous atmospheres around these satellites. And of course, I explained before how important it is to disentangle the magnetosphere and the plasma environment conditions around Ganymede. We will be doing the same thing for Europa. Of course, we want to know the composition on the surface. Like I said, the non-icy material, what is it made of? We're going to be looking at these regions where the ice crust is so small that we can look down to the subsurface liquid water, as indicated here. We're going to be trying to see if there are geysers on Europa. Some people have indicated measurements that probably show ejecta and plumes on Europa. It has not been confirmed to this day. But the very important thing is also the atmosphere and the ionosphere on which you can have oxidized components. Very important to bring into the liquid water where you have reduced conditions and then create the redox phenomenon that I was talking about before. So this will be happening during the 2 Europa flybys I just mentioned. Here is how operating different instruments, imaging, sounders, radar, fields and particles can give you both the ocean thickness and the crust thickness by looking at magnetospheric interactions, the magnetic induction, the surface deformations from an eccentric orbit, and the periodic variations of the rotation. And this is how we're going to know how deep and how thick is this liquid layer. This is what we want to know. We want to know how deep it is, how deep you have to drill, how thick it is, and what's the density. So all of this is going to be bringing us a lot of information on all of these satellites. This is a very complex system. It involves a lot of people. In Europe, for instance, you can see here all the people and all the countries that are involved. We had indications of interest from something like 20 or more countries around Europe. We had indication also from non-European countries, indication of interest. So this is really a very exciting mission for all of us. It's going to be the first time that the European Space Agency shows that they can deliver actually all alone a spacecraft of this size in the outer solar system and study the gas giant and several of the moons around it with a focus on Ganymede and 2 categories of planetary interiors with the possibility of icy water underneath it. So I'll just finish by showing you also what we could do in the Saturnian system, where we have the Cassini Huygens mission, which started 2004, going through different phases of the mission and ending in 2017. This mission will have a sequel, I'm hoping, in some of these concepts, either a new orbiter over there to look at Enceladus and Titan, a balloon. This is a mission that I managed to talk the European Space Agency and NASA to study for a couple of years in 2009, 2010. We want to put a balloon on Titan and go around the equator to study the different phenomena. A lander on the surface, as I said, on Titan, you have a liquids exposed, lakes and oceans, so you can land something, a probe on it, and they even, I don't know if you've heard about it, the submarine, the famous submarine that you go into the lake underneath the water and see what's in this liquid extent, and even an airplane, because Titan's atmosphere is composed mainly of the same thing as on Earth. What? Thank you. I never get the right answer. Sometimes people say oxygen. No, nitrogen. 95% of the atmosphere of Titan is nitrogen. Very thick atmosphere, can easily support a plane or a probe. And this way, by studying these moons, we study the water worlds I mentioned before, huge quantities in the solar system, but also in the universe. So we're in the right place now with this exploration, starting from discoveries, going through the discoveries also of the exoplanets, moving to JUICE now, exploration of a water world in the solar system, and looking in the future to future landings thanks to all of this. Just to finish by saying water is not the only thing important in the universe. You never know what other people are looking for, so we have to keep an eye open for other species. So this is the book that you mentioned before. If you want to know more about the life beyond Earth from an astronomical perspective, because I'm not a biologist, we looked at all the different objects in the solar system and beyond with my co-author, Teresa Grenaz. And so thank you very much for your attention.